Someone rolls a die across a table. It stops. One number, and that is everything you get. You have been told a quantum computer tries every possible answer at the same time. That sentence is everywhere. It is wrong. Not simplified. Wrong, in a way that hides the actual idea. And the actual idea is far better than the myth. So we will follow one single roll of that die, all the way through the machine, to the number you finally read. An ordinary bit is one of two things, 0 or 1. There is nothing in between and nothing behind it. A qubit carries a number for every possibility at once. Those numbers are called amplitudes. Everything follows from them. An amplitude is not a probability. It has a size and a direction. Every simple explanation drops the direction. 2 qubits carry 4 amplitudes. 3 carry 8. Every qubit you add doubles the count. At 300 qubits, there are more amplitudes than atoms in the visible universe. That number is real. Headlines love it. And here is the catch nobody mentions. You cannot look at those amplitudes. No instrument in the machine reads them out. All you can do is measure, and measuring destroys the whole arrangement. Everything collapses to a single answer. Which answer you get is decided by chance. The size of an amplitude sets how likely it is. Nothing else survives. A hand rolls the die again. It stops on a number. 6 possibilities went in, 1 number came out. That is the rule that governs the entire machine. Many possibilities inside. Exactly 1 answer out per run. Now, put those 2 facts together and watch the popular explanation fall apart. It takes about 10 seconds. Suppose you really did prepare every possible answer at once, 2 to the power of 300, all at the same time. Now you measure, because measuring is the only thing you can do. You get 1 answer, drawn at random. All the others are gone. The chance it is the answer you wanted is 1 in 2 to the 300. That is not a small chance. That is no chance at all. You would have done exactly as well by guessing once, with a pencil, in a second. Preparing everything at once bought you nothing. This is not a technicality. It is why quantum computing took so long to invent. Holding many states was never the hard part. The hard part was always the same question. What do you do with all those amplitudes in the moment before you look? Superposition is the raw material, not the work. Calling it the answer is like calling flour a cake. The machine is not the many states. The machine is what happens between preparing them and measuring them. And that in between is where the whole field lives. Every algorithm worth the name is a plan for that gap. Nothing else counts. So, the real question is not how to hold 2 to the 300 possibilities. It is how to bend them before anyone looks. Remember that amplitudes have a direction, not just a size. This is the moment that fact pays off. It is the whole engine. 2 amplitudes pointing opposite ways cancel each other out. Not reduced, gone. That possibility no longer exists. 2 pointing the same way add up. That possibility grows at the expense of the others. There is only so much to go around. This is interference. The same effect that makes bright and dark stripes behind 2 slits. Waves add, waves cancel. A quantum algorithm is a built sequence of steps that aims that cancellation. Every step is chosen for where it points. The wrong answers get steered into each other until they wipe themselves out. Not one at a time, all of them, by construction. What is left standing is the right answer, holding nearly all the amplitude. The machine has done its work. Now you may look. You measure exactly as before. You get one answer, drawn at random. But now that one answer is almost certainly right. That is the trick, and it is the whole trick. The machine never tries everything. It loads the die. The die is still a die. 6 faces, 1 roll, 1 number. Every rule from the beginning still holds. It is simply no longer fair, and building that unfairness on purpose is what a quantum algorithm is. For any of this to work, nothing may disturb those directions. Not a stray photon, not a vibration from the street outside. A superconducting qubit holds its state about 100 millionths of a second. Then the direction is gone. The rest is noise. Every operation the algorithm needs has to happen inside that window. All of them, in order, before the state falls apart. Someone stands before a cryostat, tall as a person. Inside, 10,000ths of a degree above absolute zero. That is colder than anywhere we have ever measured in space. It is not a luxury. It is the only way the directions survive at all. Even then, the qubits make mistakes constantly. Not occasionally, constantly, in every run, on every chip that exists. Many faulty physical qubits get wired into one reliable logical qubit. Faults are caught by comparison, not perfection. The exchange rate is brutal, and it is the number the whole field is judged by. Many physical qubits for a single useful one. And for a long time, the correction machinery introduced more errors than it removed, which meant adding qubits made things worse. That changed recently. Google's Willow chip carries 105 physical qubits. The number is not the point. They made the error-correcting code larger, and the error rate fell instead of rising, never shown on real hardware before. It fell by about a factor of 2.14 with every step in size, exactly what theory had predicted for decades. Someone reads that curve for the first time in a room full of people who know what it means. The line finally points down. It is the first hardware proof that error correction scales as it should. Not a speed record, a proof that the road exists. Microsoft and Quantinuum reported the same kind of gain, between 11 and 800 times better than raw physical qubits. But here is what nobody does in 2026. Nobody runs a whole problem on a quantum computer. Not one. They hand it one narrow bottleneck inside a much larger ordinary calculation. It is a component, not a machine you own. And now the part the excitement usually skips. A quantum computer is not a faster computer. For most work, it does nothing at all. Searching an unsorted list gets a square root speed up. Real but modest, and with error correction that shrinks to a fourth root. Several celebrated quantum advantages were later matched by ordinary algorithms. The claim moved, the hardware did not. What genuinely works is finding a hidden period, the repeating pattern inside a very large number. That is a narrow talent. It is exactly the talent that breaks the encryption protecting your bank. In 1 year, the estimates of its cost collapsed. From 20 million qubits to under 1 million. What moved was the estimate, not the machine. Someone is learning to load the die. If you want to see the next one, subscribe and tell me down in the comments below, which system should I open up for you next?